Welcome back to the third in our series of free tuning lessons. I'm Andre from the High Performance Academy, and I hope that you've been enjoying the lessons that we've brought to you so far. Now, so far we've talked briefly in our first lesson about air-fuel ratio, what that means, and how we as tuners use that to guide us with our tuning. And in our second lesson we talked about the other aspect of tuning, which is our ignition timing. Now, for our third lesson, we're going to go back a little bit and we're going to talk again about air-fuel ratio. Now, we're going to look today at how the air-fuel ratio affects both the power that our engine makes as well as the reliability. And a little bit of that comes down to some of the myths and perhaps misunderstandings that are really rampant out there in the tuning industry. And one of those myths is that if we want to make the most power possible out of our engine, then we need to run the engine at the leanest possible air-fuel ratio. And when we say a lean air-fuel ratio, that means that we're not mixing with as much fuel with the incoming air. Okay, so we're going to investigate that today, and we're going to look at the results of varying our air-fuel ratio on our mainline two-wheel drive chassis dyno, and we're going to look at the power results as we change the air-fuel ratio at wide open throttle. First though, let's take a step back, and I'll just reiterate some of the points we discussed in our first lesson about air-fuel ratio. Now remember that it's the amount of air, or more correctly, the amount of oxygen that's entering our engine that defines the amount of power that we can produce. Our job as a tuner is simply to match the correct amount of fuel to mix with that air. So from the tuner's perspective, there's not really a lot that we're doing with the fuel delivery that influences the power that the engine makes, provided we get the air-fuel ratio approximately correct. Now, remember again from our first lesson, there's two real reasons why as we increase the load on the engine, or in other words, as we apply more throttle and ask for more power from our engine, there's two reasons why we're going to start adding some additional fuel, or and alternatively, while we're richening the air-fuel ratio. The first of those is when we're at wide open throttle, we obviously want maximum power from our engine. And under those turbulent conditions with high airspeed, what we want to do is make sure that all of the oxygen entering the cylinder is properly mixed with fuel and hence can be combusted correctly. And if we do that, that's going to allow us to make maximum power out of our engine. The other part that's really critical, and this is really what we're going to be talking about today, is under wide open throttle, we end up with much more fuel and air being burned in the combustion chamber. So the combustion temperature, the temperature of the gases in the combustion chamber, the temperature of the combustion chamber itself, and the piston top all get a lot hotter. And that heat, if we don't control it, can be very damaging to our engine. So what we're doing is we're using some of that additional fuel from our richer air-fuel ratio to help control the combustion temperature, and that is the key to the reliability of our engine. So before we get too much further into the technical aspect of it, we're going to lay down a base run now with our Nissan 350Z. Now for this particular lesson, we're using our Nissan 350Z again. This time it's fitted with a Haltech Platinum Pro plug-in ECU. Now again, if this isn't the type of engine you're tuning and it's not the ECU platform that you're tuning on, remember what we're looking at here is the fundamental principles. So regardless what type of engine you're tuning, and regardless what platform you're tuning it on, whether you're tuning on a standalone ECU or you're even reflashing the factory ECU, you're going to be able to apply these same principles. So don't think that you need a Nissan 350Z and a Haltech ECU to apply what we're going to look at today. Before we do our first run on the dyno, let's have a quick look at the Haltech ECU Manager software. And here on this particular screen, we've got our base fuel table, or in this case, volumetric efficiency table. And that table is also shown graphically over here on the right-hand side. Now, at the same time, down the bottom here, we've got our target air-fuel ratio on the left and the measured air-fuel ratio coming from a wideband and the exhaust on the right-hand side. Now we're not actually going to be changing this table because we've already got the engine tuned at wide open throttle. Now if we click on our target AFR table here, we've got a target air fuel ratio table, which is the air fuel ratio we're going to want the engine to be running. And what I've done is I've highlighted the areas at wide open throttle and I've set them all to 13.0. So that's going to be our target air fuel ratio for our first test. Now it's important to note, if you've looked at our other two lessons so far, the configuration of these tables is around the other way to the two ECUs we've looked at so far. In this case, in the Haltech, we've got RPM on the vertical axis and we've got our manifold pressure on our load axis up here on the horizontal axis. And it's this area out on the right hand side that we're going to be at during wide open throttle running. So let's get our engine running and we'll see what we end up with a target air fuel ratio of 13.0. Okay, so we've got our first run complete there and we've ended up with 144.7 kilowatts at the rear wheels. Now we can see at the bottom here we've got our power graph in kilowatts, and I'll apologise to those of you who work in horsepower, but really the numbers aren't the important part. What we're going to be looking at is the difference as we change the air fuel ratio. And in the top table here we've got our air fuel ratio, which is represented by the red line, and you can see we've got a white target line sitting in here at 13.0, which was the target for that run. And you can see throughout the run our measured air fuel ratio sits very close to that target, which is exactly what we wanted to see. And it's important to mention at this point as well, when we are talking about air fuel ratio with tuning, we don't ever have a rock solid steady number. We're always going to see a little bit of variation or fluctuation in that air fuel ratio. So when I say I'm targeting 13.0 to 1, in this case I'd be quite happy with that measured air fuel ratio being plus or minus about 0.1. So anywhere between 13.1 and 12.9. Okay, let's drop back into our laptop software now, and for our second test what I'm going to do is I'm going to highlight again the whole wide open throttle area of the running, and I'm going to now target a air fuel ratio of 12.5 to 1. So that's a richer air fuel ratio. Now for the same amount of air we're going to be adding additional fuel. So we'll save our first run and we will give it a name of 13.0 just so we can reference it nice and easily after we've finished the 3 runs. Now we'll start our second run now and we'll see what sort of results we get with a richer air fuel ratio. And we're ready for our run, so we'll press go. Okay, so that's our second run there complete, and our power this time is 145.7 kilowatts at the rear wheels. Again, you can see on the dyno our red line here, which represents our measured air fuel ratio, is now tracking very close to our target of 12.5 to 1. Remember, the white line on this graph represents 13 to 1. Now the power on that run there was 145.7 kilowatts, so we saw a total difference there of about 1 kilowatt from our first run. We're going to save that run now and we'll give it a name of 12.5 just so we can reference it again later. Let's drop back into our laptop software and we're going to highlight the same area of the target AFR table. This time we're going to target an air fuel ratio of 13.5 to 1. Now for this particular engine, being it's naturally aspirated, a modern 4-valve V6 engine, 13.0, our very first run is probably in the ballpark of what I'd normally be targeting. 12.5 you could probably consider to be a little richer than what we would normally run this sort of engine, and likewise 13.5, it is probably a little bit leaner than what we would normally run. But let's just see how that affects the power that the engine makes. So we'll get the car running on the dyno into 4th gear again, and we can start our 3rd run. Right, so that's our 3rd run complete now. And for this run, we've got a measured power at the rear wheels of 144 kilowatts. And let's just save that run now. And what we can do is analyze the 3 runs together. We'll overlay them all over the top. You can see that up here on the top graph, we have our power in kilowatts at the rear wheels. And below that, we have our measured air-fuel ratio for the 3 runs. So when we look at the power, what we can see is that those 3 runs overlay almost directly over the top of each other, and at no point have we got much more than about 1 kilowatt in discrepancy between the richest and the leanest of those runs. A lot of that can also be put down to just simply run-to-run variation with the way I've been running the car on the dyno for the purposes of our demonstration. The point of the lesson though is that in order to make good power with our engine, we don't have to tune at the leanest possible air-fuel ratio. We can choose a safely rich air-fuel ratio, and it's going to give us all of that benefit of the additional fuel in the combustion chamber to help control temperature, and that's also still going to give us really good power and torque from our engine. So there's no need to be chasing the leanest possible air-fuel ratio in order to make the most power out of our engine possible. That's a really important point to keep in mind, so we can make really good power and retain really good reliability from our engine. So that completes our 3rd lesson, and hopefully now you've got a better picture of the importance of air-fuel ratio to both engine reliability and power. Hopefully that's also possibly debunked a few myths surrounding lean air-fuel ratios and engine power. So in our next lesson, we're going to be looking at some of the more advanced functions that are now possible with modern ECUs and how we can use them to our advantage. That lesson will be coming to you in your email inbox, so look out for that. In the meantime, thanks for watching.